we want to introduce the surface integral. Now we already know how to find the surface area in 3 dimensions. If I have a surface defined z equals f of xy, we took little patches on the surface when we projected it onto the xy plane, and then added all of these up, and then we scaled it over a multiplier. We knew that this was the double integral over the surface of ds, but the surface area parameter we discovered was fx squared plus fy squared plus 1 under the square root dA. So we then said, if we integrate this over the region in the xy plane, this is how we calculated the surface area. We're very familiar with this, and we've done this recently. Now suppose every point on this surface had a different density, and I wanted to find the total mass. I want to integrate over some function. Then if that function we call g of xyz, then what I want to do is over the surface g of xyz ds. This would be one way of finding, for example, the mass of this surface. Now we have a couple of issues here. First of all, we would have to replace the ds again with the surface area parameter. But secondly, we're doing a double integral and we have 3 variables. So at this point, we would need to replace z with f of xy. So this would become the double integral over the region in the xy plane of g of xy f of xy times the surface area parameter dA. Now this is how we will formally calculate the surface integral. Let's consider the following example. I want to evaluate this particular surface integral here, where our surface is the portion of the circular cone z equals square root of x squared plus y squared between z equals 0 and z equals 3. So we have to start by finding our surface area parameter. So we'll find fx, which in this case will simply be x over the square root of x squared plus y squared. Fy will be y over the square root of x squared plus y squared. Then fx squared plus fy squared plus 1 under the root would be x squared over x squared plus y squared plus y squared over x squared plus y squared plus 1. But if you notice, that adds up to 1 plus 1. This is just root 2. So therefore, ds is simply root 2 dA. So continuing, our surface integral will then be the double integral over the region in the xy plane of x squared plus y squared to the 3 halves. This is z to the 3rd times root 2 dA. Remember, z was the square root. Now this one is perfect for polar because our region in the xy plane will simply be the circle of radius 3. That's the top of the cone projected downwards. So this will give us, I'll pull the root 2 out in front, the integral from 0 to 2 pi, 0 to 3. This is r squared to the 3 halves, r dr d theta. Now we know this part here, that's simply going to be r to the 4th power. So when I integrate that, I'm going to get 0 to 2 pi, 1/5 r to the 5th. I'll pull the 1/5 in front. Evaluate from 0 to 3 d theta. So that's just going to be 3 to the 5th power, which is 243. And then when I evaluate that d theta, I'm just simply going to multiply this by 2 pi, and we will get 486 root 2 over 5 pi as the value of our surface integral.